So here we have this velocity displacement function, and we're going to work what that is as a simple harmonic motion displacement time graph. We're going to do it two different ways because why wouldn't we? The first time we're going to do it as a proof. We're going to prove first that it meets, that it's a simple harmonic motion relationship. So for a proof, we want to go back to the fundamental concept of simple harmonic motion, where the acceleration is equal to a negative omega squared x, so it's negative of a displacement function. That's in your formula sheet, and we also know that if it's, we can have it as a linear factor, where that d is the centre of motion. So we also know that acceleration is dx of a half v squared. So we're going to marry those two together and go, well, acceleration is going to be the derivative of a half of v squared, and there's v squared. So I want to do half of that. So that's going to be and we're just differentiating this with respect to x. So acceleration will be 200 minus 100x, and acceleration will be, let's go with the minus 100, x minus 2. Hey, there we have it. Therefore, it is simple harmonic motion. That proof is done. From here, we can actually see that omega is 10. And we also know that d is, the centre of motion is 2. Okay. Let's see where that gets us. So I know I've got the answer down there, but let's just... so I've got dt. Let's not use d. We're not maths B. xt equals a sine omega t plus d. We've got d is 2. We've got omega is 10. And we don't know what this a is. Actually, I'll get rid of that a because I'm going to put the number there. I want to find what that a is. So we don't actually have a anywhere there. But if we think about it, let's just go back to, this is going to be some sort of function. What we do know is that the velocity at this maximum point, when this oscillating thing is at its extremities, its velocity is 0 because it's stationary. So we know velocity is 0 when displacement is at its maximum. We're going to use that concept here, and all we're going to do is we're going to come up to this initial thing here and go plus 400. So we know when this velocity is 0, these x's will be the biggest they will possibly be. So that's just a quadratic. So let's go put that into the other side. So that will be x. That's not a plus 4, that's a minus 4. That will be an x minus 7. X plus 3. So our 2, remember x is displacement. So when I say x can be 7 or negative 3, that's the maximum displacement this thing can have from centre. It makes sense also that, see there's 2. 2 is in the middle of 7 and 3, isn't it? How far is it from 2 to 7? Well, it's 5. And how far is it from 2 to negative 3? It's 5. So what's our amplitude of our function? It is 5. So there's 5. Okay. So there is our displacement time graph showing simple harmonic motion. Okay, that was so much fun. Let's do it again. So v squared we also have from our formula sheet this v squared equals omega squared. That's hard to draw. A squared minus x squared. Now, when this x can actually be a linear factor as well, which is no problem. It gives us our centre of motion. That one in the formula sheet, the centre of motion is our axis. Okay, so really, all I want to do is pull the coefficient of x and then complete the square, and we're home and hosed. So I'm going to do that a little bit weird because completing the square with a negative in front of that x squared is going to be hard. So I'm going to pull the negative 100 off. X squared minus 4x minus 21. There we go, okay. Equals x squared minus 2. What's in the box? So it's plus 4 minus 4. There's our pattern. So it's going to be x minus 2 squared minus 25. So all of a sudden we get v squared equals, now I'm going to put that negative back into the bracket, so it becomes 25 minus, and that's in that pattern. So we can go, omega is 10, our amplitude is the square root of 25, which is 5, and our centre of motion is 2. So going this way, we can go straight to our displacement time graph being 5 sine 10t plus 2. That doesn't necessarily proves the funny things, aren't they? Have in the back of your mind that this is the fundamental concept of what a simple harmonic motion is. So if you're asked to prove that something is in simple harmonic motion, then this is the way to go. But if you're asked just to find the distance time graph of a simple harmonic motion, I reckon this second way is a lot quicker and a lot easier. Okay, that's fun. Love simple harmonic motion.